in a non-magnetic, non-collision warm plasma. When you say non-magnetic, it means there will be no external magnetic field present in the plasma fluid. And when you say non-collision warm plasma, in fact, in that case, we neglect any type of collision, that is collision between electrons, collision between electron and ion. All collisions will be neglected in this discussion. And in second case, we will consider the waves in non-magnetic collision plasma. When you say collision plasma, then we will actually take into account the collision which actually takes place. So in this first lecture, I am giving you a brief account of the waves in non-magnetic, non-collision warm plasma. And for this discussion, actually we will have to make some important assumptions. So you can see I have mentioned some of the important assumptions for your convenience here. As the heading says, that plasma is sufficiently hot and thin. Sufficiently hot and thin. And if the plasma will be sufficiently hot and thin, then it is obvious that we can neglect the collision in this medium. So the second assumption, we say that this is collision in the medium is negligible. In fact, we will apply the fluid equation, that is the Msd equation. We have already studied Msd equation in fluid description of plasma, and in fluid description of plasma or in Msd equation we also consider gravitational interaction. But in this case, we will consider that the gravitational pull acting on the plasma particle is negligible, and it is obvious that gravitational pull is actually very small, so we can neglect it. So our next assumption is that gravitational pull is negligible. And as I have told you earlier, that in this discussion we will consider that there is no external magnetic field present in this case. So you can take that magnetic field B, which represents actually external magnetic field, is not present here, and so B will be 0. Now in this type of plasma, that is the very thin hot plasma, actually wave propagation takes place just like as the sound wave propagates through air. You have definitely studied even in your +2 level the propagation of sound wave through air, and there we study actually two important equations, Laplace formula and Newton's correction. Newton's formula and Laplace correction. And you have seen that actually when sound wave propagates through the air, then Newton has assumed that the process was isothermal, but that was wrong. So Laplace corrected, and according to Laplace correction, actually the propagation of sound wave takes place adiabatically, not isothermally. It means temperature of the medium changes, but there is no exchange of heat between the wave and between the surrounding. So in this case, we just consider that when wave propagation takes place in a non-magnetic, non-collision warm plasma, then the process is adiabatic. In fact, in this lecture or in this theory, our aim is to find the dispersion relation. You know, when you say dispersion relation, actually we will obtain a relation between the phase velocity, or you can say frequency, with the wavelength. So our purpose is that. And to solve this purpose, we will start with the famous Mhd equation, which is actually called the momentum Mhd equation. You have already studied in the previous video in fluid description of plasma. I have actually described this Mhd equation or momentum Mhd equation in very detail, and so definitely I hope you can remember that momentum Mhd equation. And you can see I have mentioned that momentum Mhd equation here, that this equation says that del V by del T plus V dot del V equal to Q over M times E plus V cross B minus nu C times V plus G minus del P by rho. I hope you are knowing the meaning of every term in this momentum Mhd equation, and this V actually represents the velocity, del is an partial differential operator, you know, and Q is charge of plasma particle, M is its mass, E is electric field, B is magnetic field, nu C is actually the collision constant, and G is acceleration due to gravity, P represents the pressure, and del P means gradient of P, and rho is actually mass density, that is mass per unit volume. So I hope you know each and everything of this equation. Now let us see what are our assumptions. You have seen that our assumption says that there is no external magnetic field, and if there is no external magnetic field, it means B will be 0. As we will neglect the collision, so this collision constant nu C will be also 0. And as I have told you in the assumption that we will neglect the gravitational pull, so what will be the value of G in this case? We will take G equal to 0 or a very small, and so we simply take mathematically G equal to 0. So if these assumptions are valid, and if these assumptions will be used in this general form of momentum Mhd equation, then what this momentum Mhd equation will become, you can easily see. This term V cross B will vanish, nu C times V will vanish, this G will vanish, and so you can easily see that our Mhd equation will become what? You can see that this Mhd equation will become del V by del T plus V dot del V equal to QE over M minus del P by rho. So this is our Mhd equation. Now you know that this del V by del T is first order term, and this V dot del V is actually a second order term. You have learned while I have discussed the plasma oscillation that to solve this differential equation we make this equation actually linear, and to make the equation linear we simply neglect the second order term. So if V dot del V is a second order term, so to linearize this equation we take this second order to 0. So I have mentioned here that we seek the solution of B by linearizing this, and for which second order term is neglected. And so when we will neglect this second order term, our equation will become linear. And what will be that linear equation? You can see the most simplified version of this Msd equation after these facts will become this. This is del V by del T equal to QE over M minus del P by rho. Now first of all our aim is to evaluate this term, that is gradient of P, del P means gradient of P over rho. Our aim is to first of all evaluate this term, and as I have told you that in this case actually the wave propagation takes place adiabatically, so we can use the equation of a state for the adiabatic process. You know, in case of a thin warm plasma, we can use the equation of a state of a perfect gas, because such a plasma it just behaves like a perfect gas, and so we can use any equation of any equation for a perfect gas in this case. So you know, we have definitely studied in your +2 level that in an adiabatic process or adiabatic change, the equation of a state for a perfect gas is what? This is PV raised to the power gamma equal to constant. Here P is pressure and V is volume, you know. And this gamma is what? You know, this is actually the ratio of the molar specific heat capacities at constant pressure and constant volume. So gamma is simply Cp over Cv. You know, Cp is molar specific heat capacity at constant pressure, and Cv, this is actually the molar specific heat capacity at constant volume. So this is our equation of a state which will be applicable to such a warm plasma. Now, as I have told you, our aim is what? Our aim is to evaluate this very term, that is del P over rho. Our aim is to find this. And for this, let us take simply the differential of this equation, that is PV raised to the power gamma equal to constant. We will take its differential. So when you will take a differential, what will be your result? You can see taking differential. Taking differential. If you will take differential, as you can see, there is a product of two functions. So this will be simply differential of P times second function, that is V to the power gamma, plus first function P times differential of V to the power gamma. And what will be that? Differential of V to the power gamma will be gamma V to the power gamma minus 1 dV. You know it. And as in RHS there is constant, and you know the differential of a constant is 0, so in RHS there will be 0. Now from this equation we will evaluate the value of this dP. So what will be this dP? We will see it. So to evaluate this dP, let us take this V to the power gamma minus 1 as a common factor. You can see there will be V dP here in first term, and plus in second term there will be gamma P dV, and this is equal to 0. As a V to the power gamma minus 1 cannot be 0 because volume is not 0 and gamma has a finite value, so definitely you can say that this V dP plus gamma P dV, this will be equal to 0. And so this V dP is equal to minus gamma P dV, and therefore you can say what will be the value of this dP. This dP will be simply equal to gamma P dV over V. So this is the value of dP, that is a small change in pressure. dP means differential of P, that is a small change in pressure. Now we will introduce the density term in this equation, because our aim is to find the value of this term del P by rho. So we must do calculation in such a manner that the density rho should be included in this expression. So to include that density term, let us define the density. You know, the simple definition of density is what? This is simply mass over volume. So you can write rho is equal to m over v, or you can equivalently write it as m v to the power minus 1. V to the power minus 1. Now let us take the differential of it. So when we will take its differential, you can see this will be d rho, and this d rho, as m is constant, so there will be only the differential of v raised to the power minus 1. So what will be this? You can see this is m times, and differential of v to the power minus 1, this will be minus 1 v raised to the power minus 2 dv. And so you can write this d rho is equal to minus m V minus m over V times dV over V. I have arranged that term. Actually, there is V raised to the power minus 2, and that will be 1 over V square, and 1 over V square has been written as V times V. You can easily see from here. And so, what will be actually the value of this d rho? You can see here. This m by v, as you know, this is equal to rho. So we can write this is minus rho dv over v. And therefore, we can arrange the term in this manner. D rho over rho, this will be equal to minus dv by v. Minus dv by v. Now see the expression for dp, which I have obtained here in this equation 1. You can see, this equation should be not 1 because we have suppose this equation 1, so you should write this equation is equation number 2. So say this is equation 2. So now we will substitute the value of this minus dv by v, which we have obtained just now. So using this in equation 2, using this in equation 2, what will be our result when we will use this value in equation 2? You can see easily from here that our equation 2 will now become what? For this, see this equation number 2, this is dp equal to this much, and we will write, instead of minus dv by v, we will write d rho by rho. So our equation for dp will now become what? This will be gamma p times d rho by rho. You can see. Now, since this dp represents a very small change in p, so in the light of this result, we can easily say that if instead of this operator d, if we use the operator del, then the result will be valid. So in the light of this result, we can write that del p, that is gradient of p, will be equal to gamma p del rho over rho. Del rho over rho. We can easily write from on the basis of this equation. Now we will simplify this result to some extent. You can see here that what will be, because our aim is to find del p by rho. You can see, as I have told you earlier, what is our aim? Our aim is to evaluate this term, del p by rho. But in our calculation, we have del p, so we will simply divide this equation both sides by rho. So therefore, we can write del p over rho will be what? That will be gamma p over rho. I have also divided by rho in RHS, and times del p over rho. Now, as you know that let us say first of all this is equation number 3. This is equation number 3. Let us say. Now, you know that if n equal to number of plasma particles, per unit volume, You know that number of plasma particles per unit volume is also called particle density or number density. So I have actually used this symbol previously in several lectures from beginning, and you can recognize it. So this is called particle density, or it is also called uh, number density. Particle density, or you may call it number density. Number density. Then, as I have told you earlier, that our this warm plasma, which is very thin, behaves just like a perfect gas. So we can utilize the equation of a state of a perfect gas for this system. So, and you know, if n is the number of particles per unit volume, then what in terms of n, what is the equation of a state of a perfect gas? You know, then we can write that equation of a state will be n kb T, where T is actually the temperature of the plasma. And what is this kb? You know, this is called Boltzmann constant. Boltzmann constant. You know, it is a universal constant. In fact, usually people write the symbol K for Boltzmann constant, but here I am writing it Kb due to the fact that you will see actually after some time that in our calculation there will be the wave vector, and wave vector will be represented by the symbol K. So for not to be confused with these two symbols, I am changing the symbol for Boltzmann constant from K to Kb. And Kb is also used, you know, in several books you will find that symbol for Boltzmann constant is Kb. So Kb is Boltzmann constant, and T, you know, this is absolute temperature. So P will be replaced by this n kBT in equation 3, and again if you consider that if m equal to mass of a plasma particle, mass of a plasma particle, mass of a plasma particle, then what will be this m? Sorry, what will be this rho, not m? As you know, rho is actually the mass per unit volume. Mass per unit volume. And since in unit volume of this plasma, the number of plasma particle is n and mass of one plasma particle is m, so the total mass of plasma particle in unit volume will be simply the product of m and n. So you can write rho is equal to m into n. So after making these two substitutions, that is P equal to n kBT and rho equal to m times n, in this equation 3, what will be our result? You can easily see. Is all things okay? I think you are getting this, because this is a very simple concept. And you are familiar with all of these concepts. So now let us see what this equation will now become. So equation 3 now can be written as del P over rho equal to gamma times P, but instead of P, now we will write n times Kb times T, and divided by rho. Here I am writing rho at each like rho, and del P, sorry, here is not del P, but there will be del rho. In fact, there is del rho. You can see here, this is del rho, not del P. So this is del rho. Now we will write this rho as m times n, and over rho, and rho will be again written here mn. Here there is no need to write mn instead of rho, so I have taken this rho as rho. Now you can see that this m is mass of a plasma particle, and you know mass in classical physics is a constant quantity. So this will be outside of the operator, and when it will be outside of the operator, this m and the m in denominator will cancel out, and this n and this n will also cancel out. So what will be your result? You can easily see. This will be gamma kb T over rho times del n, and m has been also cancelled out because this m will be outside of the operator, and then the m in numerator and m in denominator will cancel out. Say this is equation 4. Now our equation is in terms of the number density n. Now we will substitute this value of del p by rho in our equation. What was our equation? You can see, you have seen earlier, in which we will substitute it. Our equation is in fact this equation 1, and in this equation 1, instead of this term del p by rho, now we will substitute that value which we have obtained just now. So use this equation 4 in equation 1. So using equation 4 in 1, we get what you will get. You can see easily that our equation, I am not showing that equation, you can see that equation again. Let us see, for your convenience I am showing that equation to you here. Del v by del t, in RHS the first term is QE by m, and the second term is minus this much, which we will substitute now. So you can say what will be this equation now. So del v by del t, this will be equal to q over m times E, and minus del p by rho, and del p by rho, you have just obtained the value of del p by rho here. You can see this is this much. So we will substitute it. So this will be minus gamma kb t over rho times del n, that is gradient of n, and say this is equation number 5. Say this is equation 5. Now our Msd equation, that is momentum Msd equation, in its simplified version is in terms of the number density n. Now again we will use another Msd equation. You have already studied Msd equation, and different Msd equation you have studied. Actually you have seen that a Msd equation which represents actually the charge conservation is given in a particular manner, and that equation is what we will see here. So again, from Msd equation, actually this Msd equation is also known as equation of continuity, you know. So again, from Msd equation for charge conservation. Charge conservation. You can remember, you have already studied it, and actually this equation is studied at several places. So you definitely recognize this equation. You have seen this equation is written as divergence of J. Del dot J means divergence of J plus del rho E by del T equal to 0. Can you recognize this? Definitely you can recognize it because you have already studied this equation while studying the Msd equation in fluid description of plasma. So, and what is this J? You know this J is actually the conduction current density, or you simply say current density. And you know this current density is related to the drift velocity of the plasma particle. And what is that expression? J is actually equal to NeV. NeV. N is again the number density, E is actually charge of plasma particle, and V is its drift velocity. So instead of this J, now you can write NeV. Is it okay? Definitely you can recognize this. This is del dot NeV. Del dot NeV and plus del rho E by del T, and this equal to 0. This equal to 0. Here rho E is what? You know this rho E is actually volume charge density. Volume charge density. When you say volume charge density, it means this is charge distributed in unit volume of the medium, and so this is called volume charge density. Now we will simply differentiate this equation with respect to t, that is time t. So let us differentiate it with respect to t. So differentiating with respect to t. When we will differentiate with respect to t, let us see here that this is del t del dot NeV plus, as in the second term you can see there is del rho E by del T, and once again we will differentiate it with respect to t. So this will be second order partial derivative del 2 rho E by del T square. So this will be del 2 rho E by del T square, and that will be equal to 0. Now you know these two operators, that is the operator del T and this del, may be interchanged. Actually, according to this equation, we will first of all find the divergence of NeV, and then we will differentiate it with respect to t. But if we first of all differentiate this NeV with respect to t and then we will take its divergence, result will remain same. So we say that according to mathematics, the interchange of the operators del T and this del is permitted, and so you can do it like that, like this. So this is del dot, and since Ne is not a function of time, so you can write it like this: del dot Ne times del V by del T. As you can say, this operator del and del T may be interchanged. So I have used the operator del t first and after that this divergence operator, and plus del 2 rho e by del t square, this will be equal to what? That is equal to 0. Now you can see your Mhd equation which we have defined in this equation number 5. So from this equation 5 you can put the value of this partial derivative of v, that is del v by del t, in that equation. So see this equation, I will directly put it because it is in my mind, and so let us see it seriously and then substitute it here. So using equation 5, so you can say using equation 5. When you will use equation 5 for the value of del v by del t, what you will get? You can see this will be del dot means divergence of del dot means divergence. So this will be Ne times. What is del v by del t? You have seen in that equation number 5. Again I am showing that to you. You can see del v by del t is equal to this much. So let us put it here. So this will be q over m times e, q over m times e minus gamma kb t over rho times gradient of n, that is del n. When you say del n, it means gradient of n, and plus del 2 rho e by del t square. This is equal to what? This is 0. Now you can see, in fact in the previous equation I have used the symbol E for the charge of plasma particle, but previously we have used the symbol Q for it. So actually this Q and E are simply same, so you can change the symbol Q by E. So as this Q is equal to E, so what will be now our this equation? You can easily see. Actually this will be del dot E times this much, but we will replace this Q by E. So you can now simplify this equation. The first term, let us see first of all, we will change this Q by E, then this will be Ne square by m, and this del dot operator will be operated on E. So our first term will be what? You can see this will be Ne square over m times del dot E, that is divergence of E. E is electric field, you know. And minus, what is your second term? You can see this is in fact this gamma kbt over rho times del n. So this del dot will be now operated on this del, and our result will be what? This will be gamma kbt over rho times Ne. See here, Ne is actually a common factor here. Ne is a common factor because you can see here Ne is multiplied to del V by del T, and this is the value of del V by del T. So Ne is a common factor. So this will be gamma kbt over rho times Ne, and del dot del n. And what is the last term? You can see the last term is del 2 rho e by del t square. So plus del 2 rho e by del t square, and this is equal to what? This is equal to 0. Now let us simplify this equation a little bit. For that, you can see here that the first term actually contains a factor del dot E. Can you say what will be this del dot E? You know, you have definitely studied Maxwell's field equations, and you know this del dot E means divergence of E. And actually, according to Maxwell's first equation, this divergence of E is equal to rho E over epsilon naught. This is Maxwell's equation, you know it. Maxwell's first equation, or you can simply say one of the Maxwell's equation this is. So definitely I hope you have an idea of Maxwell's equation in this level, definitely, because Maxwell's equation is studied before the concept of plasma physics. So definitely you have studied it, and according to Maxwell's first equation, we know that divergence of E is equal to rho E divided by epsilon naught. So now replace this divergence of E by rho E by epsilon naught. So what will be your equation? This will be simply Ne square over m, and instead of del dot E, now you can write this rho E over epsilon naught. See this, and minus rest two terms will remain at is. So this is gamma kbt over gamma kbt over rho, and instead of rho now you can write mn. You have seen that this is mass density, actually mass per unit volume, and that is equal to mn, you have seen earlier, and times Ne, and as you know del dot del, this is del square, so this will be del square n, and this del square actually you know it is known as Laplacian operator. So this is del square n, and plus del 2 rho E by del t square, and this equal to 0. Now we will simplify this result to some extent more. Let us see here. You can arrange this equation in this manner: Ne square over m epsilon, Ne square over m epsilon times rho E. This is your first term, you can see here, and minus gamma kbt over. Now you can see this n and this n will cancel out, and so here there will be only m. Now since E, which is charge of a plasma particle and it is constant, so we can easily write this charge inside this operator because it is constant. So there will be no difference if you write this electric charge of the plasma particle E inside this Laplacian. So you may write it like this: del square Ne. We can write it, and plus del 2 rho E by del t square, and this is equal to 0. Now see this first factor, Ne square over m epsilon naught. Can you recognize what is this? You have already studied it, so I am asking you, what is this? If you recognize it, and if there is a concept of plasma oscillation in your mind, which we have already studied in the previous video, so you can say this is nothing, this is simply a square of the plasma oscillation frequency. You have already seen this concept during the study of plasma oscillation. So you can say now Now Ne square over m epsilon naught. What is this? This is in fact omega p square. Omega p square. Or you can say that omega p is simply equal to a square root of Ne square by m epsilon. Can you recognize it or not? Definitely you should recognize. So if you do not recognize, go through the video on plasma oscillation. You will find this frequency. Actually, this is a very important formula which is invariably used in discussion of plasma physics. So definitely this formula should be always in your mind. And this is what? This is known as plasma frequency or plasma oscillation frequency. So plasma frequency or plasma oscillation frequency. So in our equation where there is Ne square by m epsilon naught, instead of that we can write omega p square. So what will be our this equation now? You can see this equation will now written as what you will write? You will write omega p square rho e minus gamma kbt over m times del square rho e. Why I am writing rho e? You can see here. This Ne, this is charge per unit volume, because N is number of plasma particle in unit volume and E is charge of one of the plasma particle. So Ne will represent the charge per unit volume, and charge per unit volume, you know, that is called charge density, and we have denoted this charge density by the symbol rho e. So instead of Ne, you can write this rho e, and plus the last term which is del 2 rho e by del t square, del 2 rho e by del t square, and this is equal to 0. Now you can see that this very equation is nothing. Actually this is a wave equation, and this equation represents the wave in this non-magnetic, non-collision warm plasma. So I am what will be the equation number? I have seen the equation number, but this is 5, so that will be equation number 6. So you can say this is the wave equation. You can see